Yeah, welcome everyone. Welcome to the Autonomous Systems Initiative webinars. These are free online webinars from leading academic and industry experts on the situational awareness, network autonomous systems, and human-machine interaction topics. IEEE Autonomous Systems Initiative is an initiative to bring together people from IEEE SPS society, but also from other societies who are passionate about signal processing for autonomous systems at large. And this year, we start off our first seminar from Dr. Dimitry Shutin. Dimitry Shutin obtained his PhD degree from Graz in 2006, and he's currently leading a swarm exploration group from the Institute of Communication and Navigation, which is in the German Aerospace Center. Many of you would know it as DLR. So, Dimitry, pleasure to have you. The floor is yours. Could you share your slides?
Thank you, Raj. Thanks for the introduction. So let me now share my slides. I hope everyone can hear me. Can you please confirm it?
I can hear
me. All right, perfect. Good. So now you should be able to see my slide. All right, so it's a pleasure to be the first this year to kickstart ASI webinars. So I will start the seminar talking a little bit about physics-assisted multi-robot exploration of spatiotemporal dispersal phenomena. So it's quite a long title. There are a lot of keywords hidden here, and I will try today to explain a little bit what all these keywords mean and why they come together in the title of today's talk. So as Raj mentioned, I'm working at the German Aerospace Center. It's actually a relatively big research center in Germany. We have altogether around 11,000 employees. There are a number of institutes. We have around 55 institutes that are distributed all over Germany. And institutes work in very different consider very different directions, like space, of course, aeronautics and transportation. So these are the three main directions, but also energy and security, kind of key research aspects, which DLR work with, basically research and applied research and development. We have also several offices outside of Germany, in particular in Brussels, in Paris, Tokyo, and Washington. So we're a relatively big organization. So it's not only space where we are active, but also many other domains. So the institute where I am is located in Oberpfaffenhofen. It's in a very south. So I hope you can see it here. So it's actually in south of Germany, close to Munich. It's a relatively big research center, so there are multiple institutes located here. And one of them is the Institute for Communication and Navigation, where I have a pleasure of leading a small research group dedicated to swarm exploration. And one of the aspects that we consider in our work is exploration of gases or materials that diffuse through the air. So why we want to do that? Well, what is the purpose of doing that? Well, first of all, it's a problem that has a number of relative applications. So it can be disaster management. So we might look for some leakage of gases from an unknown number of sources, and our goal is actually to identify how many sources we have and where they are. It can be pollution monitoring, can be forest fires. So there is a number of applications where the dispersion of material in the air is of interest. And since such processes are typically quite dynamic, so they change under the influence of wind, the the matters that the diffusers can also be sparsely located in the environment. We try to utilize multiple robotic platforms, we call them swarms, in order to be able to capture these processes more efficiently. So we are trying within this research, we are trying to investigate how can we better understand or characterize such diffusive processes using data collected by multiple robotic platforms. Of course, gases are very interesting, but the methodologies that we apply here can also be exploited for other applications, simply due to the fact that physics is very similar. It can be, for example, exploration of icy moons, where search for so-called smokers underwater might give an indicator of biological activity. So that's an application that is very interesting and can profit a lot from the methods that we develop for exploration of gases. Of course, we don't have to go so far as icy moons. We can also consider other applications on Earth, for example, underwater pipeline inspection and locating sources of material leaking underwater can also be interesting. And as we will see, the methods that we apply here can also be used for characterizing leakage or spillage of material underwater. So there is a number of applications that can be of interest. So how do we actually approach such a problem? So what is the general strategies that we take and that we develop in the group? So as I mentioned, we're talking about multiple robots, right? So we have multiple systems. It can be drones, it can be ground platforms, it can be sensor networks. So it's not really that important. And the first question that we ask ourselves is actually, what do we measure? And how do we model or understand the things that we measure? So you can imagine that we are talking about some kind of a facility, technical facility, laboratory, or a refinery that is relatively complicated, and we now try to understand if there is some leakage of material in the air, or if we can detect the presence of material in the air. So of course, what we do, we start with the measurements, right? So we try to take a sensor, bring it into the environment, and see whether the sensor makes a detection or not. But on top of that, we also bring a little bit of an understanding what we actually exploring, right? So if we trying to detect a gas over this technical facility, we know that the gas will be probably propagating in the direction of the wind. There is also a certain physical property of the gas. It might be heavier than air, it can be lighter than air. So we can, once we start this exploration process, we already understand a little bit about the process itself. And this is what we can use to better or to support our exploration with the robotic platform. So we try to kind of combine the measurements that we collect with the an understanding of this process that we typically bring with ourselves from expert knowledge or learn from the data in different forms. And of course, once we have a measurement and we have the model, typically, as we know in signal processing, the first thing that we do is we try to fit the models that we have to the measurements, to the collected measurements. And this is typically known as inference. However, in our case, the inference is cooperative because we do not have just a single entity. We have multiple robots or multiple sensors. So we might think also of how to do this inference in a cooperative fashion. Why do we want to do that? Well, we want to do this cooperatively in order to be able to essentially quantify uncertainty or quantify information content in our measurements. And this quantity or this quantification is important because it, as we will show, it can be used to actually define how our swarm or how our robots have to move. So we use this intermediate processing. So we use this processing results to better understand where should we go, where should we take next measurements, or where do we have to place the next sensor, so that we better understand the process we are interested in, acquire new measurements, and essentially repeat the process all over again. So we begin always with the measurements that we collect through our robotic systems. We try to understand it using some physical modeling, and we repeat this process in a loop, which effectively consists of two parts. The first part would be the inference, so we try to actually fit our models to the collected data, and the second part would be exploration and navigation. So we try to direct the robots towards the areas where that would actually help us better understand the process. So this is kind of the general strategy of the approach that we take. And throughout the talk, I will show you examples how these two parts, the inference and modeling, as well as exploration navigation, can be realized, or how we realize these components of the swarm exploration systems. At this stage, I would like to ask: is this can you see my screen? Is everything okay with the presentation? All right. So I assume that everything is fine. So I will continue. So how do we solve the first step? So how do we actually combine these modeling aspects and the measurements that we collect? And this is what we call the domain knowledge assisted gas source localization problem. This is one problem that we consider. For example, as I mentioned, we know that if we have a material propagating through the air, then its dynamics, its spatio-temporal dynamics, can be well approximated with the so-called convection diffusion equation. So what this equation explains? So this equation shows the relationship between the concentration of the gas, which is denoted by the function f, and as you can see, it depends on space x and also on time. So it's a time-varying concentration of the material. This concentration also diffuses in space, and this is the second term in this equation. So let me activate the laser pointer. So this is the second element in this equation, which is responsible for gas diffusion. So we know that the gas itself will diffuse, and if you imagine having several gas sources, you would see that the diffusion would kind of produce these three clusters of gas that kind of slowly decays from the location of the source. Of course, we also have the convection component, which essentially responsible for the transport of the materials through the space. So if you have a certain wind direction, then the gas, of course, will move in the direction of the wind. And the right-hand side of the equation, this is a function that actually represents the sources. And this modeling, the modeling of the sources, is actually quite important, as we will see later. So typically, the sources, as an individual location where the gas can come out, are in fact sparse. So we can say that the gas comes, if we are talking about, for example, a pipeline, then typically the gas would come from either a leakage point, so it will be a well localized position on the pipe where the gas is coming out, or maybe some outlet. That would kind of represent a discrete location where the gas is coming into the atmosphere. And what we can do here, we can say, well, we have a few sources that actually produce that drive the whole process. So later we will see that this assumption that the number of sources is sparse, so we have individual sources, is actually quite important, and it allows us to accelerate exploration quite significantly. So these two things, so the first is a physical-based modeling of the gas dispersion based on convection diffusion equation, an assumption that the source distribution is sparse, so that we have a few sources that drive the whole process, are essentially our domain knowledge that we would use to assist our exploration process. Of course, the other component is a measurement. So these are the first two things that that we use kind of to kickstart the whole exploration process. So we also need to collect the measurements, and in our particular case, we're talking about, first of all, measuring concentration. So taking a robot and driving into the gas plume and taking a certain concentration value of the gas, but also we can measure wind, so we can use the different sensors that will tell us in which direction the wind currently transports our material. So this is kind of the third component. So we have now a model, or in this case, a kind of a prior assumption, if you will, about the dynamics of the process, and we also have measurements. So how do we now approach the inference problem? So how do we combine the our convection diffusion equations with a sparsity assumption and the collected measurements? Well, of course, the first step is, as engineers, what we do, we try to bring this continuous descriptions of the process into some discrete form so that we can realize it on a computer. And we know from the theory that kind of the approach to deal with partial differential equations, and this is what we have here, right? The convection diffusion equation is a partial differential equation. So the standard way of dealing with that is to use finite elements or finite difference methods. So what you see here is just an example. So we use a finite element approach to discretize our equation, which essentially includes bringing an equation into so-called weak form and representing the Spader temporal function as essentially as a decomposition of a function into a functional series, right? So we approximate the functions of interest, the continuous functions of interest, with using a set of fixed basis functions, which we typically would call finite element functions, right? That are defined over space, and we do that for all functions of interest. So we do that for concentration functions. We use it to represent the source distribution. We also use it for test functions that is used in this Wick formulation of our partial differential equation for wind velocity. So all terms that are present in our partial differential equations are represented then as functional series. And the key element, as I mentioned, is this finite elements, which essentially form orthogonal basis for spatial representation of a function. And once we do that, essentially all our functions are represented with coefficients of these decompositions. So this is for those of you who are familiar with finite element methods, this is probably quite trivial. If you're not familiar with the method, that's okay. It's not important. So what is important here is that we go from a continuous representation to a discrete one using relatively well-defined steps, which essentially allow us to write, instead of continuous functions, allow us to write via representations in terms of functional series, and essentially bring all the terms in our partial differential equation into first discrete space continuous time equations, where now the kind of coefficients of our representation are continuous in time, and then using discretization in time, we finally bring it into the form that most of us are familiar with. So we have at the end an equivalent representation, equivalent expression that includes vectors of unknowns coefficients and matrices that have coefficients based on the chosen finite elements and specifically computed for an equation of interest. So we end up at the end with a finite difference equation with certain matrices and vectors that we try to estimate. Of course, we also have to do similar steps for our boundary conditions to make sure that the equation that we have is well defined. So at the end of the day, we begin. We start with a continuous partial differential equation, and we bring this model into a discrete representation, and end up with the equation that we can then implement on a computer and do simulation. Right. Similar things, of course, we need to do for our measurement. So this is the measurement model that we use for wind and for concentrations. It also have to undergo through the discretization, and essentially you can think of it. I mean, what you see here is a relatively simple example of it. So we say that the concentration measurement is given to us by some in situ sensor, which just gives us a value of a gas at a certain location. Of course, since our concentration value is now discrete, what we observe essentially a single element from our discrete vector that represents the concentration values. Similarly, the wind is also, of course, represented using finite elements, and what we observe are just certain unknown elements of this wind vector. So the sensor, the values that we get from the sensor, essentially will follow then this measurement model. And this is kind of the setting with which we can now apply our favorite inference algorithms off the shelf, or whatever methods that you would like to try, because we now have essentially a model that is discrete and that describe the process of interest, and we have now a measurement equation which tells us how the quantities of interest are related to the data that the sensors deliver. Are there any questions at this stage?
Dimitry, this is Raj. Just because you asked for a question, are there any assumptions on the noise on the between the epsilon FL and epsilon VL? Do we assume they are independent?
We assume that they're independent. Yes,
okay.
This is right. But this is in practice. This is not always the case.
Got it. Thank you. Thanks a lot.
So it's a very useful assumption, and we use it practically. But the wind and the concentrations that we would observe might correlate, and that would imply that the noises might also correlate. So in practice, this is not always the case, but for the inference methods that we use, we would like to make this assumption.
Clear. Thank you so much.
Yeah. I'm not talking about yet, at least, about the distributions of these perturbations, but in theory, you can of course assume quite different distribution for these quantities.
All right. Thanks.
All right. So how do we approach now this inference problem? Well, we would like to actually take a Bayesian approach towards inference, and one of the reasons why we prefer Bayesian approach is that we not only want to get the value of the quantities of interest, so we not only want to know the concentration value at a particular point or the source strength at a particular point. We also want to know their distribution, or at least their variances. Why do we want that? Well, essentially the variance of the parameters of interest is directly related to the information content that we have in our measurement about the parameters we are trying to estimate. And as we will see later, this information content is actually the main criteria we use for driving the robots. We are trying actually to navigate our swarms towards the directions where the information content would be increased. And that, of course, requires not only knowing the parameter values, but also their certainty. And I will come to that later. But essentially, this is our main motivation why we want to use the Bayesian modeling or Bayesian approach towards this problem. So how do we do that? Well, of course, we have our partial differential equation, what you see here now in a discrete form. And the first thing that we do, we say, well, the equation is not exactly zero. So we allow ourselves to relax this equation and allow some deviation from an inequality. And the quantities that this residuum quantity that results from this equation, we say, well, this is a random quantity. We say it's a zero mean normal with a certain precision parameter, but by assuming this residuum to be non-zero or deviate from zero and to be random, allow us to formulate a relaxed gas propagation model. So essentially, it allows us to say, what is the probability of the concentration given a certain values of wind and the location of the sources that is represented by the partial differential equations that we have. But this is now a relaxed equation, right? So it's how far it deviates from an exact equation is controlled by a precision parameter, tau sub s, but in general, of course, we can allow a certain deviation from an exact equality. Of course, we have a measurement model because we collect concentration measurements. We also collect wind measurements. And based on the statistical distribution of the noises, and again, coming back to the previous questions, based on the assumptions, whether these noises are correlated or not, we can then formulate the likelihood function. So we can say how the wind the wind values, also the direction and its magnitude, as well as the concentration of gas, are related to probabilistically related to what we observe. So that's a probabilistic description of our measurement values, which of course will formulate our likelihood description. And the classical Bayesian inference approach would tell us, well, if we want to estimate parameters of interest, and that's basically sources, concentration, wind direction, possibly conditioned on the measurements that we collect, then what we have to do, we have to take the likelihood function, which is the probability of the measurements given wind and concentration values. We need to take our model into account, in this case, relaxed model, which give us the probability of the concentration conditioned on wind sources. And finally, of course, we need to come up with some prior distributions for the wind and some prior distribution for the source. So this is kind of a standard Bayesian approach towards parameter inference. So the state likelihood is basically quite clear. So we derive this quantity from our measurement model. The relaxed model of the process or gas propagation model is also quite clear. So we relax our partial differential equation and allow some deviations from zero. So what about the priors? So these are also kind of quantities that are important. Let's begin with the wind prior. So this is one where kind of we can make a relatively simple assumptions, at least at this stage. So we say that we say that the wind is essentially a Gaussian process. So we do not distinguish between laminar flow and turbulent flow, because that would actually make a modeling of the wind quite complicated, at least within the presentation that I'm giving today. There is no this distinction. So we use a relatively simple assumption here. So we say that the X and Y components of the wind are uncorrelated and that they are both Gaussian. So in each direction, an X and Y direction of our exploration domain, we say that the X and Y directions are independent. and normally distributed. And from what we have observed, so from the measurements that we have collected, it actually seems to be quite a valid assumption. So this seems to correspond quite well and or work well in practice. And the parameters for these priors, again, this is not an exact wind distribution, right? So it's a prior about our wind distribution, and these can be typically taken from weather forecasts. So this is kind of a dominant wind direction that we use then in our analysis, and this is something that can be relatively easily assumed. With the sources is a little bit more difficult. So remember, we said that we assume that the sources are sparse. So there's a few sources. So how do we do that, or how do we cast this assumption in a Bayesian framework? We use for that a method called sparse Bayesian learning. So what is a sparse Bayesian learning? So essentially, we say if we look in our discrete representation of our sources, it's a vector, right? So it was a vector U with each element of this vector U describing the source, a possible source at a discrete position of our triangulated space. So every element in our vector is sparse in the sense that it's either non-zero, so we have a source at a certain location, or it is zero if we don't have a source. So this is kind of the modeling assumption. And the question is, of course, how do we actually find, or how do we infer such a source vector U that would have such a property? And the sparse Bayesian learning approach says, well, in order to achieve sparsity within this Bayesian framework, what you can do, you can actually model the prior for the source as a mixture prior. So you can say that for every source, you identify a hyperprior parameter that kind of controls the source, and you try to identify not only source parameters or source values that will be then placed here in this vector, but also the hyperparameter associated with the source. So what is this hierarchical prior actually, or how it's hierarchical prior working? So why this principle works in general? So let's look at it in a little bit more detail. So the hierarchical prior that is used here works as follows. So you take a particular value of the source. So this U value would actually tell you how much material is released from a source per minute. So it's kind of a source release rate, if you will. And a hyperparameter is essentially a precision that controls the probability of this source rate. So gamma sub I is a precision parameter associated with the source distribution. And of course, within the Bayesian framework, you also have to specify the prior for these hyperparameters. And within the sparse Bayesian learning framework, it's typically taken to be gamma prior. And you can recognize that if your if the P of the source given the hyperparameters is Gaussian, and the prior for the hyperparameter is the gamma, then they form a conjugate family. So you can actually compute what would be an equivalent prior for the sources if you kind of integrate these parameters out. You can do this exercise and you would find out that the equivalent prior that you put on the source is actually student T. And what is remarkable about this student T parameter is that it has probability mass along the axis. And this is actually what makes the estimator sparse. So you would actually prefer solutions where the most of the probability is allocated along the axis of your parameter space and not in between. So that's why this combination of a source with the hyperparameters or this hierarchical approach towards modeling a prior distribution would at the end result in a prior that would prefer sparse solution. as contrast to any other. Of course, the price you pay for that is that you now need to estimate these hyperparameters gamma, but that's actually the price we need to pay to simplify your life, because working with the student T PDF would be quite difficult, but instead you can work with Gaussian and gamma pri, which are actually quite nice priors to work with. So it's actually quite convenient to have this hierarchical structure, although you need to estimate additional parameters. So another example to illustrate it a little bit more, why we get a sparse solution. So imagine that you have kind of a simple linear model. So your likelihood function would look like this. So you have just two parameters, U1 and U2. And if you would use a Gaussian prior, so kind of standard priors that you would typically use in this case, you would get a posterior where the maximum of the posterior is, of course, located somewhere in your parameter space. And clearly, the highest probability, so your solution will not be sparse. So it will be located somewhere in the parameter space, so your posterior will definitely not be sparse. If you take the student T prize, the situation will be actually quite different. So the student T has this exponential form. So it's 1 over absolute value of your parameter. So this creates this strange shape. And if you now look for the posterior, in this case, you would see that most of the probability mass will fall on the axis. So you would get a solution that is sparse. So this is how the sparsity would be then achieved when we apply this concept to gas source localization. So let us now bring all things together. Once we formulated this inference problems or the posterior, the question is how do we now model it? So if we let us again look at what we have. So we have the posterior over the source's concentration, wind, and also now hyperparameters, which are all conditions on the measurements. And this posterior of interest, this is what we want to estimate. That would be proportional, of course, to our model fit, where we connect our measurements to wind and concentration values. It will be proportional also to the probability of the concentration as described by our partial differential equation. So this is kind of our relaxed partial differential equation model. And now it has these two priors. So we'll have a prior for the wind and we'll have the prior for the source, which is now constrained by these hyperparameters, which we now have to estimate. And we can cast it into a classical hidden Markov model process. So of course, we start with some initial conditions. And for the first moment of time, we have our measurements of the concentrations. And of course, we collect several of those using multiple drones or robots. We also have several measurements of the wind. These are related to the quantities of interest, which are the concentration values hidden in the variable f, the source values hidden in the variable u, and wind parameters that are hidden in the variable v. So these are the variables for the first step. And of course, our our source value u is now controlled by the parameter gamma. So this is kind of the hyperparameters that enforce sparsity. And now if we move to the next time and so on and so forth, we would essentially construct a hidden Markov process where we observe the concentration values, we observe wind values over multiple time instances, and based on these measurements, we can now, our goal is now to estimate the distributions of unobserved variables. So this is a classical inference problem, and there are multiple ways how you can do that. The way that we consider this problem is casting the hidden Markov model into actually a factor graph. So how can we do that? Well, essentially, we recognize that our joint PDF or joint posterior PDF actually, posterior PDF is just a product of multiple terms. The first is, of course, the product over the samples that we have collected. Then there is a product over individual discretization cells. And one of the ways how we can exploit the structure is given by the factor graph, which effectively captures the hidden Markov model as a bipartite graph, where we have now two types of variables. We have variable nodes, which represent variables of interest, which is in our case sources, concentration values, wind parameters, and hyperparameters, and factor nodes, which effectively capture relationship between these different variables. So we cast this hidden Markov model into the factor graph. And why we want to do that is because there are different algorithms, or very efficient algorithms, to do inference on this factor graph. So we can utilize message passage schemes, in particular loopy belief propagation, to identify values of the, or distributions, marginal distribution of the variable nodes. And this is, as you might know, includes kind of transmitting messages between factor nodes to variable nodes, and from variable nodes to factor nodes in following different update protocols. But if you do it long enough, at the end of the day, the messages at the variable nodes converge to the marginal probability densities of these nodes, and this is what we actually want to do. So this is an approach that we use to derive to infer distributions of the variables that are interest for us. And as I already said, we want to do that because we not only want to know the value of our concentration at a particular cell, we also need the distribution of it. So we want basically to know its variance. Another advantage in the factor graph is not only that we compute the distribution of the variables and also utilize the message passage schemes to do inference on such structures, is that we can also distribute the computations over several platforms. And the most straightforward ways how to do that is basically to take your factor graph and cut it into different pieces. And then what you can do, you can place every piece on a robotic platform, and instead of now sending messages directly over the factor graph, you can utilize a communication network to transmit the messages between different portions of the factor graph, and in this way implement this algorithm in a distributed fashion. So you can actually reduce the first of all, the computational complexity of this message passing, and second, you can also make the system kind of more stable against failures of individual drones, but because you can simply recreate part of the graph on different platforms, and in this way, kind of make it more robust. So let us see a small illustrative example. So we consider a simple case of diffusion from two sources. So there is no wind with so-called Dirichlet boundary conditions. So we assume that at the boundary of our domain, our concentration is 0. So we have roughly 500 nodes in our discretization. And we consider sampling at 100 different locations. So this is what you would get as a result of this inference. So you would see that this is how the concentration map would look like in a steady state. So there is no time dependency here now, and there is no wind. So you would get this an estimated concentration at a certain time instance, and as you can see, so after 100 samples, you get a relatively good estimation of the source locations, and they are located at the correct spaces, as well as the number of the sources is also correct. So it actually shows that the sparse Bayesian learning is able to recover the true locations. how can you profit now from this inference scheme to actually explore? So how can you use this factor graph representation and inference to now direct the robots toward locations which are more interesting or more profitable? So the first thing what you can do is then you can treat this probabilistic inference as essentially a black box that produces the, of course, source distribution and the concentration distribution. But of course, we know, since we have not only the value of the parameters of interest, but also their distribution, we can measure the variance at every cell of our domain. So we know how certain we are about the variables in our domain. And this certainty can be used to derive an exploration strategy. So what this strategy can be? Well, first of all, we can look at every point in our space, and we can use this estimated concentration as a gauge of information content. So the cells which give us a highly uncertain concentration values, for example, contain relatively a lot of information, because our model essentially tells us I'm not very certain about this particular point of space. In contrast, if we have a measurement of the gas concentration with a low variance, we are relatively sure that our concentration at this location is known quite well. So we are relatively certain. So we won't go to this point, but rather we would prefer a point where the uncertainty is high. So we would try to measure at a very uncertain location. So let us see how this works in simulation. So here I will show how the impact of sparsity, and also coupled with this exploration strategies, how much does it bring in terms of efficiency of localizing the source. So what we have here is a situation with two sources and a wind that drives the sources in the northeast direction. And we will compare an uninformed case, so essentially a case where we just randomly sample the space, and we do not take into account the fact that the sources are sparse. Versus the informed case, where we use the informative sampling, so we use this information-driven sampling techniques, as well as make use of the assumption that our sources are sparse. So let's see what happens after 10 measurements. So in the uninformed case, the measurements are basically randomly distributed over the whole environment. Whenever in informed case, as we can see, the measurements are concentrated along the plume that result from a single source. While we see roughly the locations of the sources in the uninformed case, as we can see, the estimate of the source strength is very diverse. So we see some indications where they can be, but there is also kind of negative sources which actually do not make sense at all. So after 30 measurements, we already see that with the informed case, one source is quite well localized, so we know already where it is. So it's as you can see, its location is known quite well, and we continue to sample along the plume, go into the second source. In the uninformed case, we basically start sampling everywhere. So there is no way in the uninformed case we see the kind of the sources appearing as a result of the estimation. After 50 measurements, informed case already has a correct estimation of the concentration map, as well as the correct number of sources. Whenever for uninformed cases, we arrive to this state roughly after 250 measurements. So we need 5 times more measurements to get an idea where the sources can be in the uninformed case, as compared to the uninformed scenario, where we need roughly 50 measurements. So we are significantly more efficient if we make use of these additional assumptions. So if we now compare it, for example, what happens if we have 5 robots? So as you can see, If we do not use the sparsity assumptions, we require significantly more time to properly reconstruct the concentration value, which we measure using normalized mean squared error. And if you look at the quality of estimating the source locations. So here we use the so-called Earth movers distance, which is better fitted for measuring quality of estimating sparse signals. Then, as you can see with the sparsity prior, with the sparse assumption, we're significantly more efficient. So we require significantly less time to identify the sources as compared to doing a same estimation without the sparsity assumption. Of course, if we are talking about real robots doing such measurements, we also need to consider robotic aspects. We need to take robotic aspects into account. So we need to think about proper planning or replanning of trajectories if there is a potential collision, or we need to plan a trajectory in such a way that the robots do not collide. So these are, in practice, of course, these robotic aspects play a significant role in bringing the exploration concepts that I have explained in practice. So here you can see one such experiment where we have 5 robots and 3 unknown sources. So it's a hardware in the loop experiment, so there is no real gas in the laboratory, but the robots implement the described exploration strategy in real time. So each robot has a small Raspberry Pi, and they solve the inference problem in real time. The only what is simulated here is, of course, the process and the measurement itself. And as you can see, after a certain time, both the number of sources as well as their location is correctly estimated, and we see that the gas concentration are also mapped quite accurately. So the method is able to work with simulated measurements and simulated processes. We also did a similar experiment with real robots and sensors. So we have now 2 sources here, and 3 robots are now moving in real time. We have as a test gas, we use alcohol vapor, which is basically something that we could test in the lab without any harm. As a robot, we used a custom-built small miniature miniature rover equipped with photonization detector sensors that reacts to concentration of or that can measure concentration of alcohol in the air. And we also simulated a little bit of an airflow with a small fan array. And the basic idea was here to test whether we can actually implement the exploration approach with real gases. And the results are shown here. So what you see after the first minute of the exploration, as you can see, there are not so many measurements. So after 1 minute, the robots were able to collect only 7 measurements. If we look at the map of the source strengths, you see that after 1 minute, we were not able to identify the source locations, but as we collect more and more data, we see that the number of sources and their location start to converge. So after 7 minutes, we have identified the first source, and after 11 minutes, the second source is identified. So we actually get a correct estimation. Of course, the method here directs the robot to the points with the highest uncertainty. So we just basically in a greedy fashion drive to the point where the information or uncertainty about the concentration value is high. And that's this approach requires additional coordination between the robots. So it requires an additional selection of the points. And that can be costly and requires additional cooperation between individual robotic platforms. And one approach that we have recently investigated is what we call the information field exploration. So here we are trying actually to use the information that we, or uncertainty maps that we identify, as directly as a criteria for navigating. So how this is implemented? Well, we assume that a robot has a certain dynamics. For example, it can drive straight along a certain direction theta with a certain, and it can turn with a certain rate. So we assume a relatively simple robot's dynamic, and we use our inference algorithm to compute at every moment of time. So at every stage of our inference algorithm, we compute an estimate of the uncertainty map. So this is what you see here on the slide. So red areas indicate areas of high uncertainty, blue areas indicate areas of low uncertainty. Clearly, you see where we have made a measurement, the uncertainty is low. So it's high only outside of our spaces where we have made a measurement. And the idea of this information field is actually very much related to so-called potential field control, where we take this computed uncertainty and we construct it, or we use it to construct an artificial potential field. And we use this potential field to essentially navigate the robot. So the areas of low potential, so where the uncertainty is high, we say this has to be attractive. So this is where the robot should, if you will, roll down. The areas of low uncertainty should be repulsive. So we don't want to go in the directions or in the areas where uncertainty is low. So that should be used to construct a repulsive repulsive areas or repulsive agents. And of course, by combining this, you get essentially an arbitrary potential functions with different areas of attraction and repulsion. And essentially what you do, you let the robot navigate this uncertainty field. So we turn in the direction of the potential field lines which drive the robots towards high uncertainty. And of course, we turn along these field lines. So we try always to go in the direction of high uncertainty. And as we move, we collect the data. And of course, that's change the computed uncertainty field. And we also tested that in experiment, and it was actually quite successful. So we tested it with 3 and 4 robots. Again, it was a hardware in the loop experiment. And what you can see here is a snapshot of how the 3 robots navigate this potential information field. So we are here seeing how the uncertainty field changes with time as we proceed. So in the first case, so this is a relatively simple model. So there is no wind. So we consider only diffusion in a single source. That is in the center, as you can see. Initially, the uncertainty is very high in the center. The boundary conditions are known, so their uncertainty is low there. But once the robot make measurements, you can see how this field is changing, and each robot automatically navigates towards the areas of high uncertainty, and in this way, as uncertainty is always reduced. So that's proof to be quite efficient. So at this stage, small question, Raj, how much time do we have?
Yeah, we have about 5 minutes more to wrap up.
All right, so let me just briefly go through some maybe a little bit advanced topic. I will just briefly mention in the directions that we are investigating right now. So one of the directions which we are quite interested at the moment is actually going gridless. So previously we assumed that the sources are located at the grid points of the discretizations that we have used, and that introduces some limitation. First of all, if you're looking for the sources, then the number of unknowns is essentially proportional to the number of the discrete points that we have. However, if we assume that we have only a few points, or sorry, a few sensors, sorry, a few sources, then the number of unknown parameters can be actually quite small. And if we try to kind of get away from assuming that our sources are located on the grid, then we can significantly reduce the number of parameters that we need to estimate. This couple of slides a little bit summarizes what we did in this direction. So one approach that we're currently investigating consists of using so-called Green's method to solve the partial differential equations that describe the gas distribution. So what you can see here is the Poisson equation, which is essentially a steady state advection diffusion equation without convection term. So it's just a diffusion term, and this diffusion is driven by a discrete number of sources. But now we assume that the sources can be located anywhere, so they're no longer on the grid. And we were able, by using this green functions method, to derive an algorithm that allow us to identify the number and locations of the sources that are no longer constrained on the grid. So let me just show you a small simulation. So for 1D, in 1D case, the solution to the Poisson equation is just this triangular shape. So if you have a source at the location 0.5, your solution, the concentration value would be just a triangular shape function. And if you have another source at a different location, then you would have a slightly changed triangular function. And based on this model, you can, again, formulate an estimation scheme that would allow you to estimate the number of the sources and their locations by not restricting the locations of the source theta to any grid. So this is an approach that we have recently developed, and let me just show you how this is realized. Again, the method uses the sparse Bayesian learning to identify the support. So it uses it estimates the sources kind of that are active by selecting from a certain set. But since we are now no longer constrained to the grid, to estimate the grid locations, we need to use some gradient descent method. We have derived essentially an expression for the gradient that allow us to kind of shift the locations of the sources and at the same time identify the true number. And what you can see here is how this simulation is working. So let me start kind of with an initial setting where we have true number of sources that are which is 3. So we have this blue lines which indicate true sources, and red lines are estimated sources. And as the algorithm progresses, we see that the sources actually moving, and the number of sources also decreases, so that at the end we have the correct number of sources at correct locations. So now there is also an extension of this method to a distributed setting where the agents essentially share only the support or the locations of the estimated sources. Let me just skip the slides and maybe go a little bit to this one, which is I think the next step that we are trying to do right now. This is an extension of the methods that we have developed with green functions to include neural networks. And the problem that we typically face with the green functions method is that these green functions are not always available. So we not always are able to compute them. And the approach that we are now investigating consists of using deep learning methods or neural networks to approximate the solution of a green function to approximate the green function of a partial differential equation. and use it as a part of the inference schemes that we have developed before. And we tried this with equations that we had, and the results that we get are actually quite promising. So what you can see here is kind of a comparison between the reference solution that we have computed and the solution produced by the neural network, and there is actually quite a good match. So we are able to learn it quite accurately. So you can see this here, this triangular functions that we have seen before. The simulation results also shows that the method actually work quite nicely. So they correspond well to the solutions that we otherwise obtained with analytical method. So there's a relatively good correspondence between kind of learned and numerically or analytically compute green function representation. And of course, the quite critical steps are going into the real world and making the experiments. I will probably skip these slides due to lack of time and go directly to some final conclusions. So I hope I was able to persuade you that gas exploration and modeling is quite a challenging problem. And the biggest problem that we have there is actually high process dynamics. So it's a very often turbulent process that changes quite fast in time and space. And it is often coupled with the fact that we cannot perceive gas with the camera. So the sensors that we're using are low information rate sensors. It's essentially a single measurement per time and space that give us a concentration value. In comparison, a camera gives you per snapshot millions of pixels that you can utilize. Of course, you can use a swarm to kind of increase the sampling rate, but at the end of the day, you need to support this kind of information scarce regime or data scarce regime with some additional prior knowledge, and this comes in terms of the physics assisted modeling. So we can kind of support our measurement process using the domain knowledge, and in this way compensate for the lack of high resolution data. There were a few results that we have now obtained using the green functions method to localize the sources in a gridless fashion. The results are very promising, but they point out that actually a combination of physics-assisted modeling with machine learning can be a very promising approach. So you can try to essentially get a little bit away from a pure physics-assisted approach, where you use convection diffusion to describe gas dynamics, or even Navier-Stokes to describe wind structure, and try to kind of introduce a data-driven aspects or parts of the model that you can train, and in this way compensate inefficiencies or deficiencies of more simple models that you can compute in real time. One of the problems, however, along this path is that real data for training is not always available, because once you go outside, you realize the wind is non-stationary. You need a lot of data, and making long measurement campaigns outside might be difficult, but it's not impossible. So you can actually go into the wind tunnel and create conditions there which are relatively stable, and where you can collect stable data for training models. Also, one aspect that I haven't discussed much in the talk, but which is practically extremely important, is robotic and robotic aspects, such as localization and navigation of robotic platforms. So these are very important for practical realization of the system. It takes actually a lot of time, but it's important and needed if we want to make sure that the method will actually work in practice. So we need to take care about accuracy of our localization scheme, We need to make sure that the robots do not collide, that they are able to navigate in the environment. So it's in practice, at the end of the day, it turns out to be a very multidisciplinary problem that we are trying to solve here. And as I mentioned in the very beginning, the methodologies that we developed here can also be applied in other domains: environmental monitoring or pollution monitoring, forest fire monitoring, or underwater exploration, so that all these applications can be addressed with the methods that we developed. So I think I would stop here and open floor for questions.
Yeah, many thanks, Dimitry. Thanks a lot for the nice presentation. I think it's a nice combination of two fields, right? So it's a source localization and robotic exploration, and I think it's a very nice bridge that you've tried to make. Any questions for Dimitry?
Yes, I do have a few.
Oh, okay. Go ahead.
Okay, so first of all, thank you very much, Dimitry, for the very nice presentation.
Welcome.
So first of all, am I audible? I just want to verify.
Yeah, you're audible.
Yes, yes.
Okay, yeah. So when you were introducing the concentration map, so I was wondering, the concentration map, if I understand correctly, that's a time varying quantity, right?
It's time and space varying quantity.
Yes. So when you're showing the results of this concentration map over time, I was wondering about, can you always accurately estimate this concentration map? Because you only have a few robots, and it is time and space varying quantity. So for all the time instances, can you always accurately estimate?
So the short question, the short answer is no. Well, first of all, in simulation, of course, it looks very nice, but in practice, you cannot do that because you have no ground truth. And this is the biggest problem, because you do not know the true concentration of a gas or material in space. So we have last year in March, we have conducted a measurement campaign in a wind tunnel where we have collected high resolution data in 3D under controlled conditions of this of the gas diffusion from a single source. And this is essentially the first time that we will have this ground truth data to actually validate our algorithms. So what we know is that in practice, the convection diffusion is a simplified but still an approximation of the true gas concentration. So in reality, there will be a certain discrepancy, because the model, there is a kind of a built-in model mismatch. And there is nothing you can do about that. Of course, you can say, I will try to model it as accurately as possible. So I will try to take like turbulence into account, but then you would leave the domain of linear partial differential equation and wander in the domain of nonlinear differential partial differential equation. You would have to deal with Navier-Stokes equation and turbulences, and this will no longer be real-time capable. So what we are trying to do, we say, first of all, we use this Bayesian approach to say there is a certain model mismatch, and this model mismatch is actually hidden in this residual term. So let me just go back fast to the models that we're using. So here, so there is this R term, which is a residual, and essentially we are kind of hiding all these aspects of these model mismatches in this term R, so in this residuum. So all short-term effects like turbulence, they will go hidden in this term. And our hope is that the model that we use captures the global dynamics, but is ignorant about a small-scale dynamics like turbulences. And this is something that the model does not capture. So therefore, the answer to your question, whether the computed concentration map corresponds or will be the true one, is no, because we know that there is a model mismatch. But on a global scale, we roughly know how it will look like. And especially if you are more concerned about estimating the sources as compared to, for example, mapping the concentration, then this might be irrelevant information. So you might not be interested in the exact value of the concentration, but rather you would be more interested whether the model will help you to localize the sources more accurately. And so far from the experiments that we have done, it looks like it works. Even in practice with simple real experiments that we did in the laboratory, where we do have turbulence and some non-laminar flow, it seems to work.
Okay. Yeah. Thank you very much. I have another question, if that's possible.
Yeah, sure.
Yeah. So if two sources are very close, will you be able to separate them?
It depends. So first of all, if you're using the first method, which effectively discretizes the space into individual cells, the question is how close are the sources? So if the sources are within one cell, then no. They will be, due to the discretization, they will be perceived as a single source. If you go for the methods that are gridless, then yes, it is possible, but again, to a certain extent. So it seems to be that you won't be able to distinguish the sources that are very close. So there is a limit to kind of this super resolution ability of the algorithm, and this super resolution abilities essentially related to the width of this green function. So if you think about two sources, so these two green functions, so they are actually quite strong. They're quite correlated. So if you think about kind of design matrix composed of or dictionary matrix composed of different green functions at different locations, and you would apply your classical sparsity reconstruction techniques, then of course such a dictionary will be highly coherent. So there is a certain limit to which you can at which you can resolve individual sources, and beyond that won't work. However, practically, that might be not that relevant. So at the end of the day, you want to maybe use a swarm of drones to inspect a pipeline. And if you can find one source that is within a cell of, I don't know, 5 times 5 meters, you would have to send there maybe people anyway to check, and whether it's just a one leakage or two leakages, practically doesn't make any difference.
Right, I see. Thank you.
Yeah, but of course, like academically, it's an interesting question how close these sources can be located. Yeah, I agree.
Thank you. We have a question on the chat from Falah, who raises the point that this is gas source localization, which is in the sparse Bayesian, using sparse Bayesian learning. Can this be applied for classification of sparse point cloud of LiDAR as well?
I would say why not? So what is the problem then in the classification in this case? So what once you get a LiDAR scan, you would get different points, and your task is then to classify whether it belongs to, I don't know, a tree or the ground. I guess, yeah, with a proper formulation, I guess you can do that.
Hello, thank you very much for the nice talk. So I just wanted to explain that my question is that we have a sparse point cloud, and we assume that each cluster of this point cloud comes from a certain object. And we want to classify the type, actually understand the type of the objects. So not in your case, localization of the gas source, but the type of the objects. So how this method can be extended to that classification problem?
Well, you can apply the SBL framework for the classification tasks. So I would say that you can do something like this, yes. But I have to admit, I do not, right now I cannot give you the recipe, but I know that the SBL can be used for classification tasks, and my intuition tells me that you can apply it to your problem as well. So I encourage you to look deeper into it.
Okay, thank you.
Thank you. Any other questions for Dimitry?
No question from my side, but I must say I'm highly impressed how you brought together all these things, and you well explained them for this interesting task. So thank you, Dima.
Yeah, you're welcome. Yeah, thanks a lot for your kind words.
Thank you once again, Dimitry, and let's close the session. And I look forward to seeing you all for the next seminar, which is next month.